Hello and welcome to eCampus. Today we are going to be attempting the OCR modeling physics paper from 2023. Uh, the structure of OCR physics papers are such that there are two sections, Section A and Section B. Section A consists of MCQs, whereas Section B consists of descriptive as well as uh, quantitative questions. So there are total 15 MCQs in Section A, and it's recommended that you should not spend more than 30 minutes in this section. So let's start from question number 1. Which row contains only scalar quantities? Um, Displacement is and momentum also is a vector quantity, so A is out. Acceleration, force, momentum, yeah, they are vectors as well. Uh, Gravitational potential scalar, kinetic energy scalar, mass. So yeah, option number C. And if you also have a look at D, yeah, we see momentum here as well. So C is the right answer. Coming on to question number 2. Forces are applied to a circular shaft of diameter D. And which diagram shows a torque of a couple? Yeah, with magnitude FD. Uh, if we have a look at here, A and D are not couples because we need equal and opposite forces. Indeed, there is a single force, whereas A, they are two unequal forces, so A and D are not couples. So we are left with B and C. If we have a look at B, so there are two forces, and a torque of a couple is force multiplied by the perpendicular distance between the line of action of force and the pivot point. So this distance. And this distance is by definition and as given, not by definition, as given, T by 2. So there are two forces, and we are calculating this for B. F multiplied by D by 2 for the first force, plus F multiplied by D by 2 for the second. So Ft by 2 plus Ft by 2 is Ft. So B comes up with Ft. For this, it will come out to be Ft by 2. So B is the right answer. Moving on, question number 3. The resultant force acting on a moving object is 0. So there is no net force on that object. Which graph shows this? So when there is no net force acting on the object, so with the Newton's second law, the acceleration is 0. And if the acceleration is 0, that means that an object is moving with a constant velocity. So C and D are out because we see these are not constant velocities. So it's either between A and B. So the slope of a displacement times graph gives us information of the velocity. Here the slope is constant. That means the velocity has a constant magnitude. Why? Because the gradient of a displacement time graph gives us information of the velocity. But here the slope is not constant entirely through the time displacement time graph. Here it's a higher slope, then it is decreasing. So the correct option is A. Moving on, question number 4. Which row in the table correctly identifies elastic limit, fracture, and UTS in the graph below? This one is the ultimate tensile strength, UTS, because this is the highest amount of stress that is being bared or that is experienced by the material. So yeah, so I think we don't need to have a look at the others because this is the only option. Where Q is mentioned in the ultimate tensile strength. Also, we know that the R is a friction point, right? And P is the boundary of the elastic limit. So P is the right answer. Moving on to question number 5. A wire of cross-sectional area is 3.9 times 10 to the power minus 6 meters squared and carries a load of 240 Newton. The strain in the wire is 0.3%. Which values of Young modulus in Pascal is correct and expressed to an appropriate number of significant figures? All right, so Young's modulus is obviously valid in the elastic region, and it's defined as stress over strain. Notice it's not percentage strain. So stress is force per cross-sectional area over strain. So force is given 240 divided by 3.9 times 10 to the power minus 6 meter square. And strain, since it's in percentage, we need to convert it to its actual value divided by 100. It's 0.003. All right. So yeah, calculating this thing, the answer comes out to be 2.05 times 10 to the power 10 pascals. But it looks like option number C, but we have to have a look at the significant figures as well, because C and D are very close. D is the rounded version of C. So we need to figure out whether it's C or D based on the significant figures given in the original information. So it's two significant figures. It's three significant figures. It's also three. So as per convention, we should go with the minimum significant figures. So we should round this off to two significant figures, and that is 2.1 times 10 to the power 10 pascals. So that's option number D. A tennis ball is hit with a racket. The graph shows the force the ball exerts on the racket. We are given with a force time graph. And what is the magnitude of the change in momentum of the ball? We are interested in delta P, or the delta in momentum. So we know that the area under the curve is equal to the impulse of a force, or the magnitude of change in momentum. Also, from Newton's second law, the force is equal to the rate of change in momentum. And from here, we can see that the change in momentum is force times by the time bracket, right? So we need to find this area under the curve of this force time graph between 0 and 100 milliseconds. So the easier way to find this is to consider these two right angle triangles here. Yeah, this is the first triangle, and similarly, yeah, this is the second triangle. I've tried to like just the indicate the boundaries. So we have two triangles and one rectangle. So we independently find the areas of these three shapes. So for the first triangle, it's a right angle triangle. So the area is half, which is a base. One square block is 2 millisecond. So base is 10 milliseconds. So 10 multiplied by 10 to the power minus 3 times by the height. Height is 45 newtons. So yeah, this comes out to be 0.225. For the second shape, we have half. The base here is 20. So 20 times by 10 to the power minus 3. And the height is the same as 45. Area comes out to be 0.45. And for the third shape, the length multiplied by breadth gives us the area. So this is 80 minus 10 is 70 millisecond. So 70 multiplied by 10 to the power minus 3 multiplied by the height, or the breadth, yeah, and that's the same 45. So the area comes out 3.15. So all of these adds to 3.15 plus 0.45 plus 0.225, 3.825 kilogram meter per second, or Newton second. So yeah, that's option number B. We can also write that here. Moving on to question number 7. So two identical spheres, each of mass 8700 kilogram, have a space of 3.6 meter between their centers. So what is the magnitude of the gravitational force they exert on each other? So that's Newton's law of gravitation for you. So the force F that they exert on each other, as per the Newton's law of gravitation, is equal to the gravitational constant multiplied by the masses, individual masses. Since they are the same, so m squared divided by the distance between their centers squared. So the gravitational constant is 6.67 multiplied by 10 to the power minus 11. Not going to mention the units here, times the mass of the objects squared over the distance squared, 3.6 squared. So quickly calculating this thing, the answer comes out to be 3.89 uh, times 10 to the power minus 4. Uh, and when we convert it to two significant figures, that's 3.9. So B is the right answer for question number 7. Moving on to question number 8. A particle of mass m and moving at velocity u collides elastically with a stationary particle q, also of mass m. Originally, the particle p moves with velocity v at an angle theta, acute angle theta, that means less than 90, to the direction of original motion, and also particle q moves in a perpendicular direction to p. This is perpendicular, yeah, it's mentioned here, with velocity w. The velocities u, v, and w are constant, so they are moving at a constant velocity. All right, before collision, after collision figures are given, which of the following equations are correct? So we are given some options and their combinations. So since the collision is elastic, so what's the difference between elastic and inelastic collisions? That in addition to momentum and the total energy, in elastic collisions, the kinetic energy also is conserved. By the definition of elastic collision, the velocity vector u should be the vector addition of velocity vector v and velocity vector w, because since the before collision and after collision, the kinetic energy remains the same. So let me quickly draw here. So this is the velocity vector v, and to its right, I'm gonna draw the velocity vector u. There's a right angle between them, and from the head of v, we're gonna draw the velocity vector u, which is a vector addition. Yeah, this one is v, this one is u. So this is by Pythagoras theorem, u squared is equal to v squared plus w squared. So this one is right. Now coming to the first and second part, either whether they are right or wrong. So u is equal to w cos of theta plus v cos of theta. So u, which is horizontal direction, the vertical and horizontal components, when we resolve a vector into its vertical and horizontal component, they should also be consistent. So u should be equal to the horizontal component of v and the horizontal component of w. So the horizontal component of v is v cos of theta plus w cos of, since this is 90 minus theta. And we can simplify as v cos of theta plus, since sine and cos are complementary angles, so we can write this thing as w sine of theta. So here it was mentioned w sine theta, w cos of theta plus v cos of theta, so u is definitely incorrect. Number one is incorrect. Now coming on to see whether 2 is right or wrong. So w cos of theta is equal to v sine theta. V sine theta is the vertical component, so we're going to see whether the left hand side is the vertical component of velocity vector w. So quickly erasing this thing. Yeah, so v sine theta should be equal to the vertical component, or the y component of velocity vector w. So w sine of 90 minus theta, and that is w cos of theta, by the same property, because they are complementary functions. So V sin theta is equal to W cos theta. Yeah, that's right. So 2 and 3 are right. So C is the right answer.
All right. During cold weather, salt is spread in roads, causing ice to melt without changing its temperature. Which statement correctly describes the energy of water particles during this process? So we know that the total energy of any material or any matter in any phase is the sum of two energies, the kinetic energy and the electrostatic potential energy. Uh, the kinetic energy is an indicator of the motion of particles or molecules inside the matter. And it can be vibratory motion in case of solids, or it can be loose or random motion in case of liquids or gases, respectively. If I want to increase the kinetic energy of a material, I would have to apply energy to it. And the most common way is through heating it up. I would have to raise the temperature so to increase the average kinetic energy. However, since the temperature is not changing here, the kinetic energy would have no effect or no contribution from the overall energy. So A and C are out. However, since I'm sprinkling or I'm spreading salt on the road, the sodium and chloride ions would react with the water molecules, and uh, the electrostatic potential energy of the whole solution, and that's called the brine solution. The whole solution would be raised due to the addition of sodium and chloride ions and the combination with the water molecules. So yeah, the potential energy would increase. So option number D.
Question number 10. An experiment is carried out to estimate the value of absolute zero using the variation of gas pressure with temperature. So yeah, the pressure and temperature are varied. The apparatus is shown here. Which variables must be controlled during the experiment? Yeah, that's Charles' law. You might have studied that in detail in chemistry, but it's also referred in the book. So when the mass and the volume are kept constant, then the pressure P is directly proportional to T. That's Charles' law. So here P and T are varied, while V and M should be constant. The volume should be constant. On the other hand, there is Boyle's law. Just for a quick recall, when the M and T, that is mass and temperature, are constant, then the pressure P is inversely proportional to the volume, and that's Boyle's law. So yeah, the volume of the gas should be constant. So C is the right answer for question number 10. Question number 11. Satellite is geostationary orbit, 36,000 kilometers above the Earth's surface. The Earth has a radius of this many kilometers. At what speed is the satellite moving relative to the center of the Earth? So the speed of satellites in the Earth's orbit can be found by the formula V equals under root gm over the radius, or the r, with m is the mass of the Earth. That's not given, but that should be in your formula sheet or the constant sheet. Uh, so quickly calculating this, g is 6.67 times 10 to the power minus 11 multiplied by the mass of the Earth, that is 5.97 times 10 to the power 24, divided by the radius, that is 36,000 plus 6,400, that is 42,400 kilometer, multiplied by 10 to the power 3 to give us in meters. The answer comes out to be 3.1 multiplied by 10 to the power 3 kilometers per second. Two significant figures. Yeah, so that's option number D. Moving on to question number 12. Four different oscillator systems are forced to oscillate at different frequencies. The graph shows the amount of oscillation for each frequency. F naught is the fundamental frequency or the undamped resonance frequency for each oscillator. The vertical axis on the graph are all to the same scale. And which of the oscillations mentioned in A, B, C, D are the most heavily damped. So, by definition, damping is the process when you apply external energy to reduce the amplitude of oscillations. And when you damp the system, the more you damp the system, uh, the more the peak of the curve shifts away from the fundamental. Or in other words, the not only the magnitude of the amplitudes are controlled or damped or reduced, but they also move away from the fundamental frequency. Uh, Let me show you a quick figure from the book. Yeah, this one. So as the system is damping more and more and more, you see not only the amplitude of the oscillations are being controlled or reduced, but the peak is shifting more and more away and to the left side of the fundamental frequency or the natural frequency of oscillation. So if we have a look now at the question, uh, option D appears to be the peak, and option D appears to be further away from the natural frequency of oscillation. So D system, or the option D is the right answer. Moving on to question number 13. During the evolution of the universe, that was a period of inflation. There was a period of inflation. Which forms of matter, if any, existed 10 to the power minus 10 seconds after the Big Bang? So these kind of questions I personally don't like, because you have to remember a lot from the whole process of Big Bang quantitatively. You have to remember what happens in the period of inflation and all that, remembering the time. So in the period of inflation, the universe was expanding very rapidly, and there was no matter whatsoever. There was only very high energy gamma photons. And we also had a look at these high energy gamma photons in connection with the microscopic background radiations. Anyhow, so in the period of inflation, there were no matter did not exist at that time. Afterwards, quarks and other fundamental particles started to form. So C is the right answer. You just have to remember this thing. Question number 14. Part of the emission spectrum of hydrogen in a laboratory is shown. All wavelengths are given in nanometer. So wavelengths are increasing here. So this is red and this is blue. Usually the electromagnetic spectrum is given in the reducing or the uh, descending order of wavelength. But here you see the wavelength is increasing. So red should be on the right side and blue is on the left side. Okay, so which diagram shows the corresponding part of absorption spectrum observed from Earth emitted from a galaxy moving away with the velocity of 0.031 c, the speed of light? A and B doesn't look like it's an absorption spectrum, so it's between C and D. So A and B are out. All right, so C and D. So since the galaxy is receding away or moving away, that means the spectrum or should be redshifted. So the spectrum should shift towards the right side or towards the right hand side. So there should be shifting somewhere on here. All of these are, by the way, redshifted. So that's it. Um, we need to recall some equations from the Doppler's effect. So for electromagnetic waves, uh, there was a very simple Doppler equation, and that was delta lambda over lambda was approximately equal to delta f over f, and this was also approximately equal to v over c. So we can use this equation. So delta lambda over lambda is equal to 0.031 c over c. So change in wavelength is equal to lambda times by 0.031. All right, so this 434 Newton meter wavelength would be redshifted to what we can say that delta lambda would be 4 lambda times by 0.031 and plus the original lambda. So we may add lambda to both sides. So 434 plus 434 times by 0.031. This comes out to be 447.4 nanometer. Similarly, the 486 nanometer should be redshifted to 486 plus 486 times by 0.031, and that is 501.1 nanometers. So this should be out of the out of the viewing window. So option C appears to be the right answer, because our particular redshifted wavelength would be around here, out of the window. So C would be the right answer. Moving on, an early estimate for the Hubble constant was 500 kilometer per second per megaparsec. What is the value of this estimate in units of per second? And 1 parsec in meters also given. So relatively simple question. Yes, 500 multiplied by 1000, and that's meter per second, multiplied by uh, 1 parsec, at 3.1 times 10 to the power 16 times 10 to the power 6 for mega uh, meters. Meter, what can call the meter? Yeah, we can calculate this thing as 1.6 times 10 to the power minus 17 per second. So the correct option is option number B.
All right, moving on to section B with question number 16. The diagram shows a road where vehicles travel at high speeds. All right, markings painted on the road surface are 40 meters apart. Yeah, this is 40 meters. And drivers are advised to keep at least two markings visible on the road between them and the vehicle in front. Okay. So the maximum speed vehicles travel at on the road is 110 kilometers per hour. The table shows data from a driving manual for a vehicle traveling on a straight horizontal road. Okay. So first part is a 2-mark question. Calculate the maximum speed V of vehicles on the road in SI units. Obviously, kilometers per hour is not the SI unit. The SI unit is meters per second. So we need to convert this 110 kilometers per hour to meters per second. So that's a very simple question. Okay, so 110 kilometers per hour. All right, so we know kilometers to meters 1000 factor. So 110 multiplied by 1000 meters, and hours to minutes and then second, that's 60 times by 60. That would be second. Okay, so the final answer would be 30.55, and we have to convert it to two significant figures, so that would be 31 meter per second. That's two significant figures, so 31. All right, moving on. A vehicle passes over one of the markings. Calculate time taken to travel the 40-meter distance between two markings. Again, that's a very straightforward question. We know that distance is a speed multiplied by time. So in order to calculate the time, we know the distance. The distance is 40 meters. And we also know the speed in SI unit, that's meter per in meter per second, 31. So the answer would be 1.29. Again, we should convert to two significant figures, so 1.3 seconds. Using the table, explain why having markings 40 meter apart helps prevent collisions. Okay, let's go to the above table. All right, so yeah, while traveling at the upper speed limit of 110 kilometers per hour or 31 meter per second, uh, we have been given some braking distance and the stopping distance. All right, and we have to explain why these markings 40 meters apart helps prevent collisions. So One instance would be obviously you driving here, two markings in between, the other car would be right here, or yeah, you may be here and the other car would be here. So the distance between you and the next car should be greater than 80, and it would be less than 120 meters. And also we know that the stopping distance, which is 96 here, uh, is the sum of two distances, the braking distance and the thinking distance. So let's start the answer. Like we know that stopping distance is equal to the thinking distance plus the braking distance. And from the table above, the thinking distance is 21 meters. Also, the total stopping distance is less than 120 meters. So the 40-meter apart markings helps the drivers in curtailing the total stopping distances within the range. You might also write there the all right. Moving on to question part B of the question. A vehicle with mass 1600 kilograms is traveling at 110 kilometers per hour. The driver sees an obstruction and applies the brakes to bring the vehicle to rest in 5.6 seconds. Estimate the magnitude of average resultant force F required to bring the vehicle to rest. Again, simple question. Force is mass times acceleration. Mass is given 1600. Acceleration is final velocity minus initial velocity divided by time. V minus u over t. Plugging in the values, 1600. Final velocity is 0 minus the initial velocity is 110. So 110 over 5.6. That gives us, in fact, we should mention the the speed in meters per second. So that should be 31 from the above calculations. That is 8,857. However, we should keep the answers to two significant figures, so 8.9 kilonewton or 8,900 newtons. Okay, moving forward. All right, explain the effect of on the distance required to bring the vehicle to rest if the road has an upward slope. So if the road has a slope like this and you are traveling here on the car, so uh, the since the weight acts vertically downwards, so a component of weight would be acting in the downward direction, right? So the distance required to bring the vehicle to rest would be lower because a component of weight, we should name it something like W sub C, would be acting uh, in the opposite or backward direction to the motion of car, and hence the total distance required for the vehicle to bring the vehicle to rest would be lower.
All right, so the diagram below shows a fairground ride. Each rider is secured in a seat suspended by a rod. The distance from the top of the rod to the base of the seat is 11.1 meter, as shown here, and the rod is attached to a disc of a diameter 7.8 meters. So to test the equipment, a sandbag is attached to the seat and the ride is started, and the combined mass of the seat and the sandbag is 12 kilograms. So instead of a human, for testing purpose, there is a sandbag. And the rod makes an angle of 35 degrees with the vertical. So it's moving at a certain velocity, and the rod is making a 35 degrees angle with the vertical, as shown here. So the first question is, one more question it is, draw an arrow labeled T on the diagram to represent the tension in the rod. So we may draw here, as we know that the tension is an axial force, so we will draw in the axial direction, and we may draw it like this. So this is the direction of tension, and we also label T. All right, that's pretty much it. Moving on to part two, I've copied the figure alongside here for better visualization. Show that the radius of the circular path followed by the sandbag is about 10 meters. So we know that this sandbag or the rider will move in a circular path like this. All right, so we have to find this radius r. And this part is already known to us. This left half. This is 7.8 divided by 2. If I use it through a different color, this red line is known to us already. This is 7.8 divided by 2. We are interested in this part, which I can refer as x. All right, so let's draw this thing separately. It's a right angle triangle. And this is 35 degrees. So then by the sum of internal angle of triangle, this should be 55 degrees to make the insides angle 180. This side is 11.1 meters, and we are interested in this side x. So using simple trigonometry, we may use the cos property. We may use the cos function. So cos of 55 degrees is equal to base, which is x, and hypotenuse, that is 11.1. So x comes out to be cos of 55 multiplied by 11.1. And always remember, for these kind of questions, to keep your calculator in degrees mode. So x comes out at 6.36 meters. But that's not the complete radius as we shown here. So radius is x plus 7.8 divided by 2, that's 3.9. So the total distance comes out to be 10.26 centimeter, 26 meter. All right, moving on. Part 3, 17a, part 3, calculate the tension in the rod. So this was the sandbag, and here was the tension T, and this is the vertically downward weight mg. So since this thing is in equilibrium at any particular instant, so the vertical component of the tension should equal the vertically downward acting weight. So this angle was 55 degrees, So we can say t sine of 55 degrees must be equal to mg. So t is equal to mg over sine 55. So mass of the rider was 12. Mass of the sandbag plus the complete package was 12 kilogram multiplied by 9.81 meter per second squared, the acceleration due to gravity, divided by sine 55. Um, that t comes out as a 143.7 Newton. Yeah, 143.7. All right, moving on. Question number 17a, part 4. All right, show that the angular velocity of the ride is about 0.8 radians per second. All right, so we have to calculate the angular velocity of the rod, this rod here. All right, so the first thing that comes to mind is the force that is acting on this ride. And since it's a moving circle, so one force that's acting on it is the centripetal force. And you know, centripetal force is the center-seeking force, so it's acting towards the center or the axis. So this is the direction. We may call it F sub c. So Fc is equal to mv squared over r. And since we're talking about the angular velocity here, we know the relation between angular velocity and linear velocity, v equals r omega. So this turns out as mr omega squared. We are interested in omega, so rewriting it in terms of omega would make it fc over mr, and taking the root on both sides would give us f sub c over mr. But the thing is, how do we find the centripetal force? Since this is the horizontal component, we can write it in terms of the tension. So this was the tension thing there. This was the force of tension. So this angle was 55 degrees. So this is T cos of 55 degrees. So T cos of 55 degrees over mr. A lot of assumptions are here. First of all, there is no other forces other than the centripetal force and the weight. So there is only one force acting in the horizontal direction. There is no resistance. There is nothing else. So yeah, this was a pretty straightforward formula. So plugging things in here, we have the tension 143.7, mass is 12, radius we found it as 10.26 meters. So omega comes out as 0.817. Yeah, we may write as four significant figures. All right, so that's yeah, that is about 0.8 radians per second. Yeah, and since the units are not mentioned, we may write radian per second. All right, moving onwards. Yeah, that's the part B. When the seat is at its highest point, the sandbag is 17 meters above the ground. The sandbag is released from the seat to model an object being dropped by a rider. And now the first part is calculate time t, which is the time taken for the sandbag to reach the ground. So this is the question of Suvat equation projectile motion. So this was a sandbag, and when it was at its highest, it was 17 meters above the ground. So this distance is 17 meters. So as it was dropped, all right, and yeah, there is a horizontal velocity and there is a vertical velocity, and there is the vertical velocity is increasing with time. That's why it's moving down, because there is an acceleration of free fall that's acting on it, and the vertical component is constant. All right, so we have to calculate the time t for the sandbag to reach the ground. So remember Suvat equations. The vertical distance is known, to us, that is 17 meter. Initial vertical velocity is 0 because the object is stationary in the vertical dimensions. The vertical component is 0. Final vertical velocity is unknown. Let me write question mark. Acceleration is 9.81 meter per second squared, and time is our prime interest. We need to find this time. All right. So if we use this equation as s is equal to ut plus half at squared, yeah, this would pretty much get our things done. Since u is 0, this part would be 0, and we can find the time t as 2 times s over a, and for t we can take the square root on both sides as 2 multiplied by 17 over 9.81, and this would give us the answer, and that comes out to be 1.86 seconds. 861. We may write, since this is a separate part, we may write it to 3 significant figures. Moving on, use your answer to A4, which was about the angular velocity. Determine the horizontal displacement as traveled by the sandbag before hitting the ground. Again, the same figure. It was 17 meters above the ground, but now we have to find the horizontal distance covered. Yeah, this is the distance that we are concerned. We know the time, since it is moving with a constant velocity, and the assumption is there is no air resistance or anything else, since it is moving with a constant velocity, so the horizontal displacement can be found by the simple formula as s is equal to the velocity, the constant velocity multiplied by time. We don't know the velocity, but we do know the angular velocity, so r multiplied by omega multiplied by time. So r is known to us, which is 10.26 or 27 actually, multiplied by omega, which is 0.817. We found it earlier, and time 1.86. So distance comes out as 15.6 meters. Yeah. All right. Moving on to the last part of question number 17. Determine with reasons the effect on horizontal displacement traveled if the object released from the right was a shoe from the rider. So now the sandbag is replaced with the actual rider, and we have to imagine that if the shoe from the rider was released, and how much horizontal distance or horizontal displacement would it cover? Well, there could be multiple answers, but the important thing is that we need to give uh, reasons from a strictly physical point of view. So the most logical answer is it would cover a shorter horizontal displacement. And why? That's an important question. Well, if we can imagine, the person would be sitting and his legs would be obviously beneath the seat, which was not the case as before. So the vertical distance would be less than 17 meters. So we can also say that the time of flight would be shorter, and uh, also the horizontal distance covered would be shorter. So we can mention some points like lower vertical distance, and that means a shorter time of flight, and that means shorter horizontal displacement. Also, the effect of drag had not been considered here. So the shoe will definitely experience drag, and that will also uh, result in shorter horizontal displacement. On the contrary, some would also say that the shoe will cover longer horizontal distance. And the reason that they would cite would be, for example, imagine this was the case with the sandbag. Now, if a person was sitting here, so if I were to draw two circles here, for example, this sand wave was moving in this circle, now that would be a larger circle. So with a person sitting on seat, the radii would be larger. So that would also mean that larger horizontal distance would be covered. So we can mention any of the statement, but the physical interpretation of this should be spot on. So you would not get any mark if you would say that it would cover larger horizontal distance, but you would mention effect of drag, or you would mention lower time of flight. But either ways, if you mention shorter horizontal distance or longer horizontal distance, the appropriate reasoning should be there.
All right, moving on to question number 18. Student is attempting to find the value of g, the acceleration due to gravity, by two different methods. The method one is the vertical drop method, measuring the time of fall of a small dense ball being dropped from rest from different heights. Whereas method number two is the rolling ball methods, where of uh, a ramp is set at different angles and the ball is dropped from a height of 1.9 meters. Single sets of results are shown below. The times were measured using a standard stopwatch operated by the student. And now compare and discuss the uncertainties of the two values of g that could be obtained using these single measurements. And describe how the student would analyze both sets of data when a full range of results have been taken. And some data regarding the height, time, and the angles are mentioned in the table below. All right. So the things that are asked from the students are regarding the comparison and discussion on uncertainties and how the data can be used to analyze for the value of G and the uncertainty in the final measurement. When answering these kind of questions, it's very imperative that you read the questions carefully and thoroughly. All right, let's start with discussion. Now, since these were single measurements, so no repetition indicates that there is uncertainty inherently present in the whole experiment. So no repetition means uncertainty in the experiment. All right, and now we should also have a look at the individual uncertainty present in the values. So there is 0.01 meter uncertainty here, plus minus obviously, and then is 0.01 second, 0.001 meter, uh, plus minus 1 degrees, and plus minus 0.01 second. So we have mentioned the uncertainties, so that's also an important point. Writing down the individual uncertainties, for example, there is 1 centimeter uncertainty in height, uh, 1 millimeter uncertainty in the length of ramp. Mention individual uncertainties. Also, um, that the uncertainty in t should be doubled. Why? Because the calculation of g would be through some sort of super equations, like for example, s equals ut plus half at squared. So squaring the involves, in order to calculate the uncertainty in t squared, you should double the uncertainty in t. Also, um, uh, I think that's pretty much it for the discussion. Now, part now the part come for the comparison of the two methods. Okay, there is separate space present to answer this one, but I think it's easy to see the values and then compare the two methods. Um Obviously, we see here that the ramp has a larger time of observation and the length. So the percentage uncertainty would be lower. Larger time and length slash height of fall means smaller percentage uncertainty. Also, uh, when we are comparing the two methods, we also see that the effect of friction. Obviously, there will be friction in the vertical drop method. There will be uh, air resistance or drag, but the surface resistance or the what we say the friction due to the rolling of ball, the rolling friction is much higher than the air resistance. So friction would be larger or higher for rolling method. Also, we would see that the uncertainty for drop height and length of the ramp are different. But we have already mentioned while mentioning the individual uncertainties here. So that's a given. Um, Another thing is that the calculation of G using rolling method involves a sine function. And now the uncertainty in sine function itself, like it's difficult to quantify, but the uncertainty is angle we have already mentioned is plus minus 1 degrees. So that's another way of comparing the two methods. Moving on, now it's time for the analysis. How would the student analyze both sets of data? Um, Analysis. All right, first thing would be the utilization of Suvert equation. I've already mentioned there. S is equals ut plus half a t squared. Since the initial velocity is 0, the equation would be reduced down to S equals half a t squared. In order to find the value of G, the student would use different values of S and T to find G, and then finally take the average of all the readings. Um Different values of S and T to find G, and then take average. Now, in order to find the percentage uncertainty in the final G value for both methods, the student would compare the S equals half gt squared with the line equation. This thing can also be written as t square is equal to 2 over gs, and where 2 over g is the slope, the gradient. With t square on the x-axis and s on the y-axis, different plots, different points would be taken, with obviously their uncertainties in the values. And now, finally, the uncertainty can be determined graphically using the best fit and worst fit line method. The best fit line goes through the center. I'm going to try as best as I can do to draw the line by hand. You should be using a ruler. And this is the best fit line. And the worst fit line can be drawn like this. You can choose a bottom value of one end and the top value of other end and the other way around, for example, or this. Well, obviously, this might not look as bad as this. The gap between the worst fit and the worst line is too high, but just an indicator how the student should go on to find the percentage uncertainty. When the slope of best fit and worst fit line has been found, then the percentage uncertainty can be found as best fit gradient minus the worst fit gradient divided by the best fit gradient multiplied by 100. So that's how you're going to go about the analysis section. All right. Moving on to question number 19. Describe how to find the center of mass of a two-dimensional object, two-dimensional shape, including any equipment required. Well, the most common method to find the center of mass of any two-dimensional, maybe irregular shape object, is to suspend that object and let it come to rest, and then using a plumb line mark the vertical downward. I might depict it using a figure. For example, this is the irregular shape object. uh, Using any external equipment, I will suspend it and let it come to rest, and then using a plumb line I would draw the vertically down, and then I would repeat this thing from multiple times, and that point of intersection would be the I assume that this is a point of intersection. I'll try it again. Yeah, and that point of intersection would be the center of mass. So multiple steps involved in here. uh, Suspend the object, and allow it to come to rest. Then using plumb line or plumb bob, draw vertical down, repeat from different points, and the point of intersection is the center of mass. All right, moving on to question number B. Figure 19 shows a bridge. The bridge can be raised by an electric motor to allow tall ships to pass underneath. Here is the bridge. All right. The moving section of the bridge is 14-meter long and has a weight of 120 kilonewton. The center of mass of the structure is 6.3 meters from the pivot. Here it is. All right. So what do we have to find out? Calculate the average power required to raise the bridge to a vertical position in 90 seconds. All right. So power is work done per unit time. And how do we find the work? Work is force multiplied by distance, and that's not just any distance. This is the distance covered in the direction of force, or that is the parallel distance covered. So force is given to us. What were the data? Let us see once again. Yeah. The force is 120 kilonewton, that's acting vertically downwards. Multiplied by distance. What is the distance? Let us see from the figure. All right. So a number of students would do this mistake. So is that parallel distance 6.3? Because a number of students confuse that with moments. So 6.3 is this perpendicular distance, this distance. But we are not interested in the perpendicular distance. We are interested in the uh, distance covered in the direction of force. So this center of mass is raised to this point. So this is 6.3 and this is 1.3. So the parallel distance or our distance of consideration is 6.3 plus 1.3. So that is 7.6. Putting that into the formula and dividing by time, the power would come out to be, let me just quickly calculate, 10,133 watts. Yeah, that is, and if I were to uh, drop it down to the actual significant figures, that would be 10 kilowatt. All right, moving on. Why the actual electric motor used to lift the bridge uh, has the maximum power output several times larger than the value calculated in B1. So they are asking, um, in the actual real world design, if I want to do the same amount of work, the motor's rating is way higher than 10 kilowatt. There are multiple reasons for it. The first reason might be that obviously the motors are not 100% efficient. There are winding losses, there are material impurities, and there are eddy current losses and all that. There are so many losses out there. So the motor's efficiency is not 100%. That's why the rating is kept higher, so that the effective power uh, uh, is sufficient as per requirement. So motors inefficiency. Although this would give us 1 mark, but a number of other reasons can be there. They obviously our calculation doesn't account for the drag, the wind loadings, or any. For example, there might be some frictional losses in the bearings and all that. So that has not been included into the calculation. So we may write loadings, losses, etc. are not accounted for. I think that's it. All right. Moving on to question number 20. A sealed container contains n moles of an ideal gas. The gas has pressure P, absolute temperature T, and occupies volume V. The mass of 1 mole of the gas is m. Using an ideal gas equation, show that the density of the gas is given by the expression this. Looks like a pretty straightforward derivation. Let's try to attempt it. The ideal gas equation is PV equals nRT, the most relevant ideal gas equation. Uh, Also, we have been given that the mass of 1 mole of the gas is m. That means that the total mass of the gas inside the container is number of moles times by m. Um, Also, we see this time density, so we may use the density formula, which is pretty straightforward. That is mass per unit volume. And if we plug in the value or the expression of um, volume from the ideal gas equation into the density one, we would get nRT
divided by p, and we can shift it to the numerator, p. Also, we would now plug in the value, or again, sorry, the expression of mass in terms of the number of moles from here. And number of moles would cancel out with the numerator, and we have the expression pressure, uh, mass of 1 mole, R and T as required. Moving on to part B of question number 20. An airship has a cabin suspended underneath a gas bag inflated with helium. The airship is floating above the ground and is stationary. I'm sure this would be used somewhere. The volume of the gas bag is 12,000 meter cube. The temperature is 20 degrees Celsius. Atmospheric pressure is 100,000 pascals. The molar mass is this much. And the volume of cabin is negligible compared to the volume of the gas. Yeah, that's again important. The gas bag. If you try to recall the actual shape of the airbags, it's a very big gas bag compared to very small cabin. So that's quite right that the volume of cabin is negligible compared to the volume of the gas bag. Now, first part, one more question, show that the density of air under the condition described is about this thing. We will use the formula as mentioned above. That density is equal to pressure, which is 1 times 10 to the power 5 times the molar mass of air, 0.029, divided by the constant R, which is 8.31, times T, and T should be in Kelvin. So 20 plus 273 is 293. This would give us 1.191 kilogram per meter cube. And to two significant figure, this is 1.2. And moving on. In fact, we should calculate the weight of the air displaced by the airship. Um, the weight of air displaced can be calculated by calculating the mass of air displaced. And since we know the density, it can be calculated pretty easily. The mass of air displaced is equal to the density, which is 1.19 multiplied by the volume, which is 12,000. And this comes out to be 14,300 kilogram. And if we want to find the weight would be simply mass times by 9.81. So the answers come out to be 40283. And to two significant figures, that is 1.4 to the power 10 to the power 5 newtons. All right, moving on. Explain why the weight of air displaced by the airship has the same magnitude as the weight of the airship and its content. Since we know that the airship is stationary, that means the net force acting on the airship overall is 0. So the forces acting in the upward direction must equal the forces acting in the downward direction, and the forces acting on the leftward direction must equal the forces acting in the rightward direction. So upward, downward, leftward, rightward, They all balance each other because the object is stationary. So the force acting downward is the weight. Uh, so the force to counter it, because the airship is stationary, so the force to counter this, which is happens to be the upthrust or the weight of air displaced by the airship, should equal each other. Since it's in equilibrium, so net force should be 0. That's why weight equals upthrust, or the weight of air displaced by the airship. All right, moving on. The pressure of the helium in the gas bag is maintained at a value only slightly greater than the atmospheric pressure. That is why larger pressure is not used. Well, if a larger pressure is used, or the pressure of the gas bag is increased, obviously the volume would not increase because of the physical limit. Uh, and if the volume is not increased, the upthrust would not increase. So there is no point in increasing the pressure beyond a certain point. Uh, Upthrust would not increase as pressure increase. So no point in increasing pressure. Also, increasing pressure would uh, also um, also increasing pressure would increase the chances of a failure due to stress. Structural failure. I think that would suffice. Moving on. The airship engine drives a fan which moves 7.8 kilograms of air per second at a relative speed of 45 meters per second. So the airship starts to move. All the conditions B remain the same. Calculate the thrust that the engines produce. Thrust that the engine produce can be found by um, the mass flow rate multiplied by the velocity. Yes, the force or the upthrust is equal to the mass flow rate, which is the delta m over delta t multiplied by the speed or the rate at which the air or the matter is moving out. So 7.8 multiplied by 45. That gives us 351. And if we round it off to two significant figures, it's 350. Or 3.5 times 10 to the power 2, sorry. The airship has a higher maximum speed at higher altitudes, but also produces less thrust from the engine. Explain these observations. Well, we know that at higher altitudes, the density of air is less than as compared to density of air at lower altitudes. So since we know that the upthrust is directly proportional to the density, that's why at higher altitudes the thrust is less. Density is lower. That's why upthrust is also low. Also, since this is a 2 mark question, we might as well explain one more observation. Um, if the engine produced less thrust with all the same parameters as before, we can also say that there might be more air resistance. Air resistance or drag. Yeah, that's it. I think that would suffice. All right, moving on to question number 21. Uh, Figure 21.1 shows a stationary glider of mass m on air track. The air track refers to a track where there is no contact friction. The mass is not in contact with any surface. Rather, they are connected using spring, and the medium or the fluid through which it is in contact with is normally air. The glider has identical springs with force constant K attached to each end, which are secured to fixed post. All right. The air track blower is turned on and the glider is displaced by a small distance x naught. Here it is. The glider moves horizontally in simple harmonic motion. That's important. The spring remains in tension throughout the motion. Okay, and the time taken for 20 complete oscillations is measured and the period t is calculated. Okay. The relationship between the time period t and the mass of glider m and force constant is described by this equation, and show that the equation above is homogeneous by reducing the equation to SI base units. Uh, the homogeneous equation is the one which is consistent in terms of units on both sides. So we just need to reduce the equation on left hand side and the right hand side in SI base units and prove that the equation is homogeneous. All right. So the left hand side of the equation is quite obvious. It's a time period, and we know that the time period unit is time unit second, SI unit is second. So left hand side unit is second squared. Right hand side, if we have a look at the right hand side, 2 pi squared is a constant. So and m is the mass and k is the constant. Uh, Mass's base unit is a kilogram. And if we talk about kx, if you remember the Hooke's law, F was equals to k times x. So k can be mentioned in terms of force and the displacement. So force is measured in newtons, whereas the displacement is measured in meters. And if we further simplify it, and would move on to the numerator, kilogram times meter over force. Force is mass times acceleration, newtons, kilogram, meter per second squared. Kilogram would cancel with this kilogram, a meter would cancel with this meter, and we would be left with second squared. So the uh, units, SI base units, on the left hand side and the right hand sides are consistent. So this equation is homogeneous. Moving on, explain why the magnitude of the resultant force F on the glider is given by F equals 2kx. All right, so in our case of an air track, this mass is connected to 2 springs on either side. And when a small displacement is done, for example, this mass is moved to this side, so the spring on the left hand side would be stretched or extended. Or in other ways, we can say that the spring is extended by some displacement x. Whereas the spring on the right hand side is compressed or the extension is reduced by x. So just for the reference, I mentioned the two distances. Obviously, the distances might not be measured in this particular regard, but just to give you an idea that if we see in terms of extension, on the one side of the mass, the extension is increased by some distance, and on the other side, the extension is decreased by the same distance. That's why the total resultant force on the glider is the sum of the two forces. And we can say the resultant, let me go back to blue, the resultant force on the glider is the sum of two forces. And obviously the extension and compression are opposite in sign, so F total would be equal to kx minus the minus kx. So extension and compression, this would overall give us 2kx. This would answer the question. State and explain the effect, if any, of increasing the initial displacement x, that's also called the amplitude, on the period of the subsequent motion. All right, so if we go to the original equation that was given to us of the time period, t square was equal to 2 pi squares times m over k. So it appears that the time period is independent of the amplitude. So time period t is independent of initial displacement or amplitude. So it will have no effect. All right, moving on. Masses are added to the glider and the measurement of 20 time periods is repeated and the results table is below. All right, mass in kilograms, then time taken for 20 time periods, one time period, and time period squared. Describe describe two different errors in the table. Okay. All right. So one that can be seen straight off is that the significant figures or the uncertainty information is not consistent. Here we can see four significant figures, then it's two, then it's three, again three, and then four. So the information regarding, even within the column, the information of significant figures or the uncertainty information, the is not consistent. So information of uncertainty, significant figures is not consistent. If we can mention something here and then here, so it's not consistent. All right, let's go for the second one. Okay, the units of t and t squares are not mentioned. It should be mentioned as s and s squared. So again, the units of t and t squared are not mentioned. All right, moving on to the second part. Plot the first data point from the table on the graph below. The other points, plot the first data point from the table on the graph below. The other points have all been plotted. All right, and the table of results is repeated on the opposite page. Include on your graph a line of best fit. So we have to plot the first point and then draw the line of best fit. All right, so what was the first point? 0.2 kilogram and 0.372 second squared. So the mass, just for the reference, was 0.2 kilogram and time squared was 0.372 second squared. First of all, we need to identify what the markings on x and y axis are equal to. We need to it would be helpful if we write them down separately. Uh, all right, so there are 20 horizontal markings or 20 square blocks between 0 and 0.2. So that means one horizontal marking on x-axis is equal to 0.01 kilogram. And similarly, for the vertical side, again, yes, there are again 20 markings or square boxes between 0 and 0.2 on the vertical side. So again, one horizontal, one vertical marking on y-axis is equal to 0.01 second squared. All right, going back above, we needed to plot the point of 0.2 kilogram and 0.372 second squared. Uh, all right, so 0.2 kilogram is this straight line. I might use uh, this line to show. All right, and for 0.372, this would be 0.39, 0.38, 0.37. So this should be something around here for the 0.372 point. So that point of intersection, which I can draw using the red color, is our point 0.2 and 0.372. All right, the next point is to draw the line of best fit. For the line of best fit, again, you should use a ruler to draw it as close to the actual points as possible. Again and again, the consideration should be to keep the number of points above and below the line equal. Again. All right. So this is the line of best fit. Uh, we can see that the number of points above the line and below the line are approximately 2 points above the line, 2 points below the line, and the distances approximately are also quite consistent. So I think this is a pretty good line of best fit. Later on, in order to remove any ambiguity, we may remove these reference line and only keep the plotted point and the line of best fit. Use the graph to determine the value of k. All right, the equation for t square was given to us. T square equals 2 pi uh, 2 pi squared m over k. So the plot is given. On the x-axis we have the mass, and the y-axis we have t squared. So if we compare t squares 2 pi squared over k times m to the standard uh, line equation, y equals mx plus c, the slope part can be correlated as 2 pi square over k. So we can use the graph to find the value of k if we can find the gradient from the line drawn above. So from the line above, we can determine the gradient So the gradient comes out to be 1.25, and plugging it into the value to find, plugging it in this and plugging it into this equation to find the value of k as 2 pi squared over 1.25. That comes out 15.79 Newton per meter. So that is the answer. When the initial displacement is increased, one spring increases its extension while the extension of the other spring decreases. Explain why the maximum kinetic energy of the motion increases. All right, so we know that the total energy is the sum of uh, elastic potential energy plus the kinetic energy. And we also know that elastic potential energy is equal to half k kx squared. And if uh, initial displacement is increased, that means that the maximum EPE, elastic potential energy, also increase, as the EPE is maximum at the amplitude. Also, we have seen this figure where we see two inverted parabolas, and we see the displacement, that is minus amplitude, the plus amplitude, and the zero. We know that this point EPE is minimum. This curve was for EPE, and this curve was for kinetic energy. So from there, and from also that the total energy is sum of both things, we know that if the EPE is increasing, since the amplitude is increasing, therefore the KE also increases. Kinetic energy also increases as EPE max is increasing. Therefore, and also we can also say uh, that the velocity, maximum velocity, which is given by the equation omega a, and since the amplitude is increasing, the velocity max is increasing, and therefore we can say that the kinetic energy max also increases. So these are some intuitive points. We can mention them one by one. That the total energy is the sum of kinetic energy plus potential energy. And since EPE is increasing, which is maximum at the amplitude, because we are increasing the initial displacement, that means elastic potential energy would increase. And since these energies are often change form during the to and fro motion of simple harmonic motion, kinetic energy also increase. And also kinetic energy increases because the maximum velocity is increasing. So I think that's it. That explains why the maximum kinetic energy of the motion would also increase. All right, moving on to question number 22. A star has a mass similar to that of our sun. Describe how the position of this star on a HR diagram changes as it evolves. Okay, and a blank HR diagram is given. You may add information as part of your response. And further, figure 22.2 shows the relative intensities of different wavelengths of light in the spectrum of a star is given. This has to do with the Wien's displacement law. Explain how the information could be used to suggest the stage of the evolution of the star and describe the limitation of the analysis. So let's start with the question regarding the HR diagram. All right, so since it's a black diagram, we have to add information uh, to supplement our response. If you remember the HR diagram, something temperature is increasing in the leftward direction and luminosity increase in the upward direction. So uh, here were the white dwarfs, and somewhere here was the main sequence, and here happens to be our sun, and obviously since the star is similar to that of a sun, the other star would also be here. Then here were the supergiants, sorry, the red giant, and the supergiants happens to be here. So this is just an indication of what the HR diagram suggests. regarding the temperature and luminosity of different stars. So quickly, let's label it for the response. These were the white dwarfs. And this is the main sequence. And different stars based on their temperature and luminosity, they happens to be a different location in this main sequence. And this is the star under consideration. This is the red giant and supergiants. Okay, so I'm going to mention the response here alongside because it's difficult to scroll up and down. Uh, when the star under consideration runs out of the fuel, runs out of hydrogen, the fusion start to happen in the subsequent layers, and the star swells up and become a red giant. I'm going to mention the same information that I just mentioned. When the star, and since it's a not so massive star, its mass is less than 10 solar masses. When this star swells up, sorry, when this star runs out of hydrogen fuel, the fusion starts to happen in the subsequent layers, in the outer layers, due to increasing gravitational pressure. And the star swells up and become a red giant. Gradually, the red giant begins to shed off its cooler layers from the outside. In fact, we should mention the number here as we are writing it down. Gradually the star begins to shed off its outer cooler layers as planetary nebula, and crosses the main sequence again, and then finally settles down as a white dwarf. Cooler outer layers are shed out as planetary nebula, and since mass is less than the Chandrasekhar limit, which is 1.44 solar masses, the star ends up as white dwarf. So this happens to be the position we have mentioned it number wise. First, the main sequence star become a red giant. Then the outer layers are shed off and its temperature rise. The cooler layers are shed off, its temperature rise, and it crosses the main sequence again. And since the mass is less than the Chandrasekhar limit, it finally settles down as a white dwarf. All right, moving on. The question was regarding the explanation on how the information could be used to suggest the stage of evolution of the star. All right. So the information regarding the intensity and wavelength are given. So Wien's displacement law can be used to model any stellar object as a black body. In fact, it can be used on even mammals or different other objects that emit electromagnetic radiations. So it can be used to model any stellar object. uh, as black body, and it suggests that the maximum wavelength that it emits is inversely proportional to the temperature. And also lambda max times the T is a constant. So if we have to use this particular graph regarding the wavelength and relative intensity to suggest the stage of evolution of a star, we have to find out the relative intensity against the peak wavelength. Now, that's one of the limitations. We will mention that separately as well, because the data of intensity is not given. We would not be able to determine. But if it was given, then we would be able to find the stage of any particular star or stellar object from the HR diagram. Evolution stage against lambda max. In fact, against the luminosity can be found from HR diagram. All right, so there happens to be some limitations. One of the limitation, as I just mentioned, is no luminosity data is given. So we would not be able to tell what is the intensity that this particular stellar object is emitting. So we would not be able to tell what is the actual evolution stage of this object. Secondly, we would not be able to distinguish among same temperature stars, for example, white dwarf or a red supergiant or a main sequence star. Another limitation is that the light from background galaxies, other galaxies in the background, would also hinder our analysis. That's it, I think, and that should be sufficient. The Hipparcos Space Telescope used stellar parallax with a precision of 9.7 times 10 to the power minus 4 arcseconds to determine the distance to stars. One of the stars studied was Polaris A, and the data about this star is in the table below. All right, estimate the maximum stellar distance in parsecs that could be measured using Hipparcos. So the maximum stellar distance would be 1 over the maximum precision of the telescope, that is 9.7 times 10 to the power minus 4 arcseconds. That would give us 1031, and rounded off to two significant figures, it is 1000 parsecs. Now calculate the percentage uncertainty in the calculated value of the distance to Polaris A. So we have to find the percentage uncertainty in the calculated value of the distance. The precision, we have been given the precision plus the parallax angle is also given. So percentage uncertainty is 9.7 times 10 to the power minus 4 divided by 7.5 times 10 to the power minus 3 multiplied by 100. The answer would be, yes, rounded off to two significant figures again, 13%. All right, moving on. A continuous stream of particles called a solar wind flows from the surface of the star into the surrounding space. These particles include helium nuclei of mass 6.6 times 10 to the power minus 27 kilogram. Assume that the atmosphere is modeled as an ideal gas show that the typical kinetic energy of a helium nucleus in the atmosphere is about 10 to the power minus 16 joules. Well, since we have been given the liberty to model this in an ideal gas, we can say that the mean kinetic energy of the helium nuclei would be 3 by 2 kT, where K is the Boltzmann constant and T is the temperature of the atmosphere around the star. So plugging in the values, 3 by 2 multiplied with 1.38 times 10 to the power minus 23 and times that temperature, which is given as 4 times 10 to the power 6 Kelvin. So the answer comes out to be 8.28 times 10 to the power minus 17 and rounded off to two significant figures, 8.3 times 10 to the power minus 17. That's quite close to 10 to the power minus 16. Moving on. And the gravitational potential energy of a helium nucleus in the outer layer of the star is minus 2.3 times 10 to the power minus 16. Calculate the gravitational potential energy U at the maximum distance from the star that a helium nucleus could reach. Well, if the gravitational potential of a helium nucleus in the outer layer is minus 2.3 times 10 to the power minus 16, and the mean kinetic energy is 8.3 times 10 to the power minus 17, then the gravitational potential energy at the maximum distance from the star could be found by their simple addition, like minus 2.3. The minus sign is important because it is the work done. It has to be, the work has to be done on the particle plus the mean kinetic energy. The answer comes out to be rounded to two significant figures again, minus 1.5 times 10 to the power minus 16 joules. All right, moving forwards. Calculate the distance from the center of the star reached by this helium nucleus. So as part of the solar flare, this helium nucleus is like spreading outwards into the atmosphere, stellar atmosphere. We have to find the distance from the center of the star that this helium nucleus can reach. So the force of attraction, the Newton's law of gravitation, the force of attraction between two massive objects was given by the gravitational constant multiplied by the two masses over r squared. And since we are given with the gravitational potential energy, uh, multiply with the radius r on both sides, we can find that the u is equal to minus gmm over r, where u is given to us. The minus sign of u would cancel out with this thing, and we will be left with gmm over r equals 1.5 times 10 to the power minus 16, where the mass of the star is also known to us. The mass of helium nuclei is also known to us, it's given, and the radius r, or this distance r basically between the 2 points, this is the distance, maximum distance where the helium nuclei could reach. A comes out to be, plugging in the values, uh, rounding off to two significant figures, 3.2 times 10 to the power 10 meters. All right, explain why the star has a solar wind that reaches a much greater distance from the star than found in 3. Well, our main assumption was that we assumed an ideal gas, and while during the assumption, it's a given that each particle of that solar flare contained the same mean kinetic energy. So in actual, obviously, there is a distribution, Boltzmann distribution, that different elements tend to follow. So a few of them might have had higher kinetic energies that go outside or that go much greater distance from the star. So simply we can write that some particle will have greater Ks. than the mean kinetic energy. All right, I think that's it. That's the end of the paper. I hope that you guys have learned something during the video and this helps you in preparation of your exam. In case you have any question or I might have done some mistake, then do let me know in the comments and subscribe us for more such videos. Thank you so much.